afternoon, everyone. My name is Chenyu Wei. In this talk, I'm going to present our recent study, modeling study on self-assembly of short peptides in membrane and how they would mediate ion transport. The transport of ion across membrane is very important for the biochemical functions. However, the insistent permeation through the membrane is not energetically favorable. The energy barrier can be 20 kcal per mole. So usually it will need some help. It needs either ion transporter or ion channels, and it can not only lower the free energy barrier, it can also provide selectivity and regulation. However, different than in the contemporary ion channel, which has very high sequence requirement and has very high ion selectivity, we expected that in early ion channel, the length and the sequence requirement is rather minimum and the ion selectivity is rather weak. So to understand the early ion channel, the formation of it, we use rather a model system. The model ion channel we try to use is formed by antimicrobial peptides. It is rather short. It has only 8 to 20 amino acids, and it is amphiphilic peptides. And lots of experiments had found this type of peptides can permeabilize membrane and have ions and small molecules and vesicle content leakage. One of the well-studied antimicrobial peptide formation of ion channel is this alamycin peptide. It has a length of 20 amino acid, and it is long enough to span the membrane and has well-defined conductance. However, we want to study something even shorter, so we are trying to understand if the peptide is much shorter than alamycin channel, can it mediate ion transport through membrane? So the peptide we choose to study is this called tricogene peptide. It has only 10 sequences, and most of it is hydrophobic residue, and it has few glycine residue on it. And this peptides is rather have a helical conformation in membrane. It can either in transmembrane state or it can be in a surface bonded state, and they are interconvertible. And experiment has found that this peptide can permeabilize membrane and at a certain peptide to lipid ratio, and even ion transport has been observed. However, the mechanism of ion transport is very vague, so people propose various mechanisms such as deformation of membrane due to the peptide, maybe the ion channel formation, maybe there are water defects. So our study is mainly focused try to understand this. We use modeling method. Basically, we use atomic molecular dynamic simulations, and to accelerate everything, the process, we also use accelerated simulation, which can lower the free energy overall in the system, so we can study a long time scale of the process. So we first try to understand with even just one single peptide, a monomer here, how would it affect the membrane structure. So we found that with this transmembrane orientation of this single peptide, it's already induced the local membrane thinning effects and introduce water defects from both sides. And such deformation is shown to lower the water free energy crossing the membrane by 1 kcal per mole. And the water transport through the membrane is found highly favorable in the neighborhood of this peptide. However, to think about this, whether such deformation can induce ion transport, the possibility is rather low, because for ion to transport easily, it needs a much larger water pore. So to continue to understand it, what we did is that we have more than one peptides on the surface membrane. As you see on the far left side, that's our initial configuration when we started the simulation. We have 14 of the tricogene peptides initially as a membrane surface. Because we want to study the ion transport, so we apply electric field across the membrane. So with the simulation progress, we see that the peptides some of them began to adopt this transmembrane conformation, and they began to aggregate. And various aggregation state has been found. They can be dimer. Actually, there are two types of dimer. They can be trimer and tetramer. And with even longer simulation, we found a pentamer structure on the snapshot we taken from our simulation on the right side, the most right side. So this pentamer structure actually is well defined. If I check the cross-section of this pentamer structure as shown on the top, it is actually behave as a barrier-stave model. It has this glycine, which is slightly hydrophilic residue facing the lumen of the oligomer structure, and also there are water pore going through the oligomer. And we observed ion conductance through this water pore. And however, I have to mention that such oligomer structure, although it can conduct ions, it is rather transient. So not only it can form pentamer structure or trimer structure, it can disassemble back to its original disordered structure. So it is a dynamic, very dynamic aggregation. Yeah. So if we want to try to understand a little bit about how this oligomer is formed, what's the mechanism for the formation of the oligomer. So quantitatively, there are two steps for it formed. On the right side, on the left side, you can see if I have two peptides inserted in the membrane, and each of them can cause local membrane deformation, and to reduce the total free energy of this surface of the membrane deformation, these two peptides is tend to aggregate, and such total free energy is dependent on the surface tension. It's dependent on the bending stiffness of which lipid you are using. It also depends on the membrane spontaneous curvature of the lipid. So the second step is that once the two peptides get close enough, they will adjust to each other and have a sequence-dependent oligomer structure. So in our case, we have the glycine residue facing the lumen of the pentamer or the oligomer structure, and so which is favorable for the water pore crossing it. So we found that actually there are more than just the oligomer structure have this ion channel-like structure. Actually, the lipid can also be induced to have a flip-flop motion across the membrane. So due to the water defects induced by this short peptide, the head group of the lipid can go through a flip-flop process going from one side of the membrane to the other side. And during this process, it can introduce a transient water pore, and through this transient water pore, ion can transport through the membrane also. So this is kind of similar as people have been long proposed as this toroidal pore for some activity of antimicrobial peptides. So this kind of confirms that it is possible. So experimental-wise, what people have been observed in the antimicrobial peptide is that people do find some ion channel-like activity, and people also, through recent years, people have been used STM image to try to understand the structure of this pore. However, I have to comment that because different than the contemporary ion channel that people can study the structures through X-ray or NMR, because of the dynamic nature of this short peptide, so it's very extremely challenging to capture the real structure of it when it's in the action. So in conclusion, we have studied the short peptides self-assembly in the membrane. We found it can mediate ion transport through various ways, and we found that the short peptides can form oligomers, different oligomer structures through the membrane-mediated formation. We found that transient water pore can be formed through the pentamer structure, and ion can be transported through such structure. We also found that membrane structure can be disrupted by peptide-induced lipid flip-flop, and also ion transfer is observed through such process. So what's the implication of our study? So it shows that short and simple amphiphilic peptides is capable to permeabilize the membrane. So it suggests that maybe select peptides, they can be candidate for the precursors for contemporary ion channels. So this is some good indication for that. That would be conclude my talk. Thank you.
Thank you, Chenyu. We have time for many questions. Go on.
Just I think some background information that might be interesting to myself and others in the room. Where does this peptide come from, and what are those non-canonical amino acids that were called AIB and LOL, and how tolerant is this to substitution? Does it have to be this exact sequence, or something that looks like this is good enough?
Oh, okay. So this standard amino acid is called amino isobiotic acid. So it has fungi nature. So it is generated post the translational process for the standard amino acid. So
It's a post-translation modified version of isoleucine?
yeah, kind of like that. Yeah. So regarding whether we can substitute it with other amino acids such as standard amino acid is a little bit hard to say, because one is that positive answer is that it is possible to replace it with a the other standard hydrophobic peptides amino acid. So because the main function of it is hydrophobic property. And the other side unique about this amino acid is that it is a helical conformation promoter. So as you can see in this specific sequence, it has lots of AIB residue. It promotes the helical conformation of these peptides. So when people substitute it with other, for example, hydrophobic residue, this might take into account whether it can influence some of its properties of this peptide. Yeah.
Okay, thank you, Chenyu. Our next speaker today is